we've come a very long way. Just a little bit more and we'll finish this project. Right now I've increased the blocks per grid to 8 and it in fact works. We still need to test whether it works with the beta being something other than 0, but we'll get to that later. What we've done here is tremendous. I have to admit, I didn't think a matrix multiply would take this long, and it was actually far more difficult than I thought it would be to create. I understand now why getting something like this from a library is the recommended path. But nevertheless, we managed to do it. This way of doing the matrix multiply should already be fairly efficient, but it could be made more efficient still. Right now, what we've done is with these accumulator fragments, by having the accumulator and the C fragments in local memory, we've decoupled the tile size from the warp sizes. If we went a step further and also loaded the K dimension into memory, we could have everything. We could work on everything just from local memory. Now where is it? Yes, or this thing here, for example. If we moved from loading the fragments directly from shared memory as they come to doing them ahead of time, what we could do is load what we could do is load the upcoming tiles into shared memory, while the matrix multiplies are being done on the data in local memory. And that could speed up the computation by as much as 2 times. We're going to do that next. It might seem daunting to do data pipelining, but we've already done all the difficult parts. Most of them, that is. In order to actually implement that, the most important thing that we still need to add to the library would be the lookahead loops. And we are going to do that next. If you're wondering what a lookahead loop is, consider this normal loop, for example. It just gives us the indices here. But in order to do data pipelining, we need 2 extra pieces of information. The current index, which is this. We also need the next index, if there is any. So that would be an optional index. And we also need a boolean for whether the loop iteration is the first, that is, whether it is initial. Once we do that, we'll be able to do data pipelining without much difficulty. So let's start work on that next. And after that, we'll finish the third example. That would be this example here. For our own function, we won't actually be needing the CUDA pipeline. Instead, we'll be using cooperative groups. While thinking about the problem, I realized that the pipeline is actually unnecessary because if you think about it, we'll be first loading the data into shared memory and then into local memory. And then we'll issue another load into shared memory while the data we are working on is in local memory. So we don't need, for example, extra shared memory tiles to hold the data. We'll first load it into local memory, and while the data is stale, we'll issue the instructions for the next load to start. And that will work really great. I mean, okay, let's just admire this for a bit and consider how much more complicated this is than our own version. Admittedly, our own version with all the dimensionality reshapings isn't the easiest thing to understand either, but it's actually the easiest possible thing to understand. The way we've written it here, for example, this thing here, this is actually the easiest way of understanding the matrix multiply. If there is a simpler way of doing this, I'd like to know about it. Of course, our own version compared to this version has a bunch of global constants and only works on 512 by 512 matrices. The first matrix also needs to have the row column layout, and the other matrix needs to have column major layout. And it's not possible to vary that. It's not possible to do the transposes. It also uses a very weird scheme, which is a lossy way of adding the beta to the final result. Instead of using async memory copy instructions, it does this manual copy back into global memory for whatever reason. I mean, no matter how I look at it, this is not a particularly good coding style. If they wanted to do the proper job in C++, they do everything that we did in this video, which is to create a proper tensor class as well as proper partition class, and then operate based on that. Using cooperative groups on top of that would also have made things a lot easier for the authors. I can't imagine how difficult getting these exact offsets was. I definitely wouldn't want to be one to write such a code. Okay, let's stop dwelling on this and get started on the next section. I am very sick and tired of working on matrix multiplies for so long, and just in just a step or two we'll be finished with it. After that, we'll be able to benchmark the various methods, the various functions, to see how well they perform. And this will be a good time to introduce the Nsight, was it Compute or was it platform? I forgot. But basically it's a profiling tool for benchmarking CUDA kernels. And we'll cap this video off by showcasing it. Stay tuned for more.
station that is unavailable at this time. Please try again later.
All the US presidential hopefuls.
There is a change in feedback so as not to lose a single voter. I agree there should be change to that added.
Okay, we're finally done with these matrix multiplication kernels, and it's time to move on to testing. What we'll do is go through all of them, from tensor 1 to tensor 8, and run them with Nsight Compute. Nsight... Actually, the Nsight Systems is the one that we need to use for benchmarking. I've never really used it before, so it will be a novel experience. Okay, first of all, let's close all of these pin tabs. We don't need them anymore. And we'll check out the previous project folders. This is the main reason why I kept them around. The tensor one, I'm not actually sure what it's for. I think I did the global kernel in tensor 2, and this one, I'm not sure what it's doing. Let me think about it for a bit. Okay, this one is actually pretty simple. This is the very first example that we did, and these are the constants that were in the original Kota-rocK kernel, I mean file. We didn't end up using most of them, but it's actually pretty easy to read. We have the reshaping, and it's pretty simple here. We'll set the number of grids to 1 actually. The only thing we really care about is how fast the individual block is. The threads per block, what was that? Threads per block, warp size. So this is 256. That's fine. In our last example, we'll also be using 256, so it's all okay. Okay, but in that case, we should make use of the entire SM. So we'll set this to 6 then. What we want to do testing these examples is performance per single SM. And for my graphics card, that would be 1576 threads, which corresponds to 6 blocks being launched in a grid. Yeah, I wish the later examples were as easy to read as this one. Anyway, let's also we'll set the sizes to 512. We'll also set the beta to 1. That's the way we should go. This particular example isn't using shared memory, but it is instead loading the fragments directly from global memory in a very inefficient manner. So I expect this kernel would be pretty slow. We'll see what the profiler or whatever this application is says about that. Okay, first let's try compiling it. I'll do that right now. And it's compiled. I'll run it just once. And we'll try running it with this thing here. I'll stop narrating here and go into time-lapse mode. It will take me a while to figure out how to properly make use of this program. And while that is happening, you just enjoy the music. The programming should be mostly be over. It's only in the last example that we'll fiddle with the tile sizes, because right now we are using two very large tiles, and that ends up using too much registers, which get spilled into local memory. So that will slow it down hugely. And by lowering the tile size, we'll be able to make better use of existing memory. We'll see how it goes. Right now I still haven't decided what I'm going to use as a baseline. A good option would be to use the kublas functionality that's already present in the QPy. This is just as a, it's this thing here. It just does a simple call from the host. But I'm going to have to figure out in that case how to make use of TrueFlow32 data types and tensor cores, because right now I think it's doing the matrix multiplication with 32-bit floats, and that would be a lot slower than a version that uses the tensor cores. We can also know that it's not using the tensor cores because the error is so high compared to our own version. I mean, the numerical inaccuracies are so high in our own version compared to the kublas matrix multiply here. We'll have to figure that out. Once we do, we'll be able to use this QPy matmul as a ground truth for how much the optimal algorithm could get in terms of performance. But for now, let's just collect some data. You enjoy the music. I figured out how to run the profiling, to not all the way yet. Instead of creating that crappy script, what you can do is this. Get the direct location of the Python interpreter and then call it directly with the matmalpy script. You also need to set the working directory to the one that you need. In case you're wondering, the way to get the source of the Python interpreter is something like this. If you just type get command python, then you'll get the source here, but not in its entirety. It will be cut off by an ellipsis. So just in PowerShell, get command python and then access the source attribute directly. Then you have this thing here, and you can copy it using the right mouse click. Then you just paste it here. And you can run the profiling with this. But it isn't working properly. Okay, we'll wait a few seconds until it finishes. and I'll tell you what the problem is. The problem is that it doesn't show the CUDA kernels that are being run. We have this GPU thing here, and the local resident memory, no local resident memory. Basically just these three fields, but we don't have the kernel itself. If we wanted to get the kernel itself, we have to run it from the command line for some reason. Yeah, we have to run this nsys profile python matmult py. I actually had to add it. This executable to path manually, so I could run this command. In case you're wondering, it's right over here. Since the previous session, I also installed the latest version of this, since it was crashing constantly. Anyway, it compiled and it generated a report. It should be yeah, I don't think it ran properly. Let's delete this thing. Then we'll cd control space and then we'll run the thing. Now the file, oh, here's the file. We'll copy the path. We go back to this thing here. We'll open it. Actually, I already have it open here. I mean the relevant directory, but you can also copy paste it into the file name. And if you look into the processes, there's the CUDA hardware, and we can see the actual kernels now. And here's the entry 0. This is our own. There's a bunch of other ones, but they aren't very noteworthy. I mean, I'm not sure why it's showing nothing in the timeline. I guess it's just because we are running a small amount of blocks. Oh, here are the fucking kernels, thank God. I mean, I have no idea how I missed them here. Okay, basically this thing isn't too useful to us. I understand now what this program's function is about. If you're running, for example, a lot of streams and a lot of kernels, that allows you to basically see where on the timeline these kernel launches are and how long they last. But we just want to compare our own kernel to the CuPy one, which I'm guessing is this. Actually, no, it's not gen sequenced, but the Ampere sgem. And compared to that one, it seems, as a rough estimate, our own is like much slower. So maybe we could get better performance if we compiled it so it launches the most kernels that it can. Let's give it a try. What the hell? We'll use the entire GPU. Okay, we have this is 6 grids, 6 blocks per grid is enough to saturate one SM, and my RTX has 24 streaming multiprocessors. We'll save this and compile it. I just pressed Control F1. And okay, let's try running the profiler again. We don't actually need this thing now that we know where the kernels are on the timeline. We can correct the memory usage. This one we don't need since we aren't using what was it called? Dynamic parallelism. Let's give it a try. Grid size will be reduced. It seems we've exceeded the device limit for some reason, but that doesn't really matter. We see the memory usage, static memory usage, generate seed pseudo. Okay, for some reason, okay, our entry 0 is only 33% compared to 12.3% for the Ampere SGEM. I'm really not sure how this works, because we increased the amount of blocks per grid. I mean, we've increased the blocks launched by something like 5 times 4, which is 20 times. And we only got like 2.5 better performance, 2.5x better performance. Okay, that basically covers how to use this profiling tool to actually launch. It's finally time to do the benchmarking. I've actually gone ahead and done it yesterday, and I'll go over the results. They are pretty disappointing. The only changes that I made to the code is to put these loops around the matrix multiplies. And as you can see, it generally calls our own gem, general matrix multiply. It also calls the one that comes with CuPy, so that can act as a baseline. All the dimensions have been set to 512, and transposes are false and true for every example, unless I made a mistake. This average here is just a loop. It sums up the errors and averages them out. Now for the results. It's a bit hard to see what's what, but they generally go in the order of they've been created. Our entry 0 here is our own, and the Ampere sgem is the matrix multiply from CuPy. It's calling the cuBLAS functions under the hood. And the figure that's important is this minimum here. The cuBLAS is around 40 microseconds, and our own is 140 microseconds here, so it's about 3 times slower. As we go along, this one is even slower for some reason. You'll see that the SGM is generally around 40 microseconds in all the examples, but our own vary. I think this is also okay. Let's check it out. What's tensor 2? Oh, this one actually uses a shared memory, I think. And in fact, you'll see this is generally a problem. It doesn't really result in a noticeable improvement. We're going to have to figure out why that is. But for now, let's just roll with it and go through all the examples. This is the shared memory example. Tensor 3 is the cuBLAS DX example, and it works horribly for some reason. I have no idea why the results for it were so bad. Let me show you. I mean, we are not going to be using it, so I'm not going to bother figuring out why it only gets 736 microseconds compared to the 40. This is a lot slower than even the naive tensor core example, which gets us 120. Basically, this is unusable. Going forward, for this one we get about 80. Let's see, but this should be tensor 4, I think. Oh yeah, it's also a shared memory example with the low tile sizes. Generally, the low tile sizes seem to be working better. And this is the example that we've refined into something better as we went along. Let's go to tensor 5. This is also a shared memory example. Let's just go forward. I just go through all of them in turn, so you can roughly see what the results are. This one gets us 70 microseconds, and this is generally the best we can do out of all the examples. Some of them do better, some of them do worse. Oh, this one is worse for some reason. Basically, I don't want to go through the old examples and try to figure out why they so slow. In fact, some of the earlier examples work much better than this one. This is the asynchronous version. The only problem is that it actually isn't correct, and I will show you what is happening. If we go to tensor 7, let me just close all of these. I mean tensor 8. We need to go into tensor 8. And now, if we go into matmul.py, let's see, is this the example? Yeah, as you can see, the error here is very large, indicating that the kernel is incorrect. I've done some playing around. Wait, not this one. I've done some playing around, and when the beta here is set to 0, and I also need to adjust it here, so this C body isn't being added, then the results would in fact be correct. But another way to get the correct results would be to go into base, and comment and enable the asserts by commenting this out. This no debug macro disables the asserts with the theory that the performance should be better with them not being enabled, but instead it ends up making the entire thing incorrect. Let me do a quick demonstration of that. I've just compiled it, and if I run it, as you can see, the results are correct now. And what's going on here is that we are running into some kind of undefined behavior. That's the only explanation for this, because the asserts themselves shouldn't affect the code being executed at all. They shouldn't affect the correctness of the code being executed, but they in fact are doing that. So the undefined behavior is the only thing that comes to my mind. And if you think about what could be causing it, the main thing that comes to mind would be the shared memory pointers. We have the pointers to the A and the B shared matrix. We also have the pointer to the C shared matrix. And as you can see, the A and B and the C matrices are overlapping. And we also have this this restrict pragma. This tells the compiler that none of the pointers should be overlapping. I thought that maybe this was just for the global pointers, but it could also be affecting the internal pointers. Let's try commenting it out. I'll compile it again. Actually, I also need to comment out the macros. I mean, comment in. Now, let's try compiling it. I'll first just erase all of this, save it. Now I'll compile it, and the reason why I've done this is so I can be absolutely sure that it's using the up-to-date version. And we still get this error, so I guess this restrict thing wasn't the culprit. We're going to have to debug this. Let's do just a little bit right now. We'll do it live. Let me disable these unused servers. This one is... ooh, what's going on here? Oh yeah, it's... never mind. I'm just curious whether moving this thing here to where it used to be. And then let's do a wait. I mean, do we do it like this, or do we put it like right here? Let's start doing it like this. I'll just press the compile key and go into matplotlib, and let's see whether anything happens. Yeah, now it's correct. And we still have this these ndebug commented out. So this is some kind of data race, but I'm confused why it is happening. I wonder if for some reason, I mean, previously it was here, but at the end of it, you should trigger this wait thread sync block. So I'm not sure why that is not happening. Maybe the async memcopy tensor is not getting hit for some reason when it's here. Let's try putting it. I'll cut it and put it back in here. Then I'll save it. Then I'll compile it. I've just compiled it, and then yeah, it's incorrect again. But for some reason the error is not as bad. Well, let's try moving this. Actually, let's try commenting this out. Why is the comment key? Okay, now it's finally working. Let me try compiling it again. The error is a lot worse. Okay, so basically, based on this, the only thing I can conclude is that there is something wrong with this statement. We're going to look into that next inside the time lapse. Then we are going to go into Nsight Compute and really drill into what's going on in this kernel. We're going to go back to the basics. We're going to pare this down to something that, for example, just loads the data into shared memory and then copies it back into global memory. And we are going to use this as a baseline for the matrix multiply. we need to figure out why exactly our own version is so slow. Because it's very slow right now, and it doesn't really make sense for it to be this slow compared to the reference gem from the kublas library. So it's not quite the final stretch that I've hoped for. We still have a lot of work left to do. But after that, we'll be able to move on to working on the machine learning library. We'll learn something from this, definitely. Let's go forward. Okay guys, let's get started. I spent quite a lot of time on Saturday trying to figure out what the error was. And it turns out there was missing a sync block statement right here on line 292. I was really focused on trying to figure out what the error was in here. I put pretty much wait sync statements everywhere, this wait thread. I tried putting it inside these if statements, like over here. And at first glance, it seems like the error goes away. But once I try to run it with the compute sanitizer, let me show you real quick. This is how you run the compute sanitizer. It comes with a CUDA toolkit. It's used for detecting data races and synchronization errors. This tool, generally, when I try to run it, it manages to induce the error that you see at the bottom, right where the cursor is. Right now, the program is working correctly, so you don't see it, and that's good. Anyway, it took me a lot of messing around, and I finally figured out that the missing block was missing here, almost by accident. For some reason, the sync block isn't necessary here, even though you'd expect it would be. My guess is that only one async operation can be in flight for each thread. That's why it isn't necessary. Also, let me show you one thing. It's kind of a weird result. Okay, finally blocked it. And if I unblock this, and now if I try to compile it, it should have been compiled just now. And if I run it with the compute sanitizer, you should see the error. And this sometimes happens because, and it was driving me insane. I make some changes. I thought I had to fix the error, but if I try to run it multiple times, it would show that the error is still happening. And it's still happening. Just a second. Okay, the errors are really crazy here. If I run this with the compute sanitizer, with this wait sync commented out, this is what loads the C matrix from global to shared, I think. Actually, it loads from shared to local. And we need to wait on the thread for it to finish this. When I comment this out and run it with the compute sanitizer, I actually get the correct result, which I shouldn't be getting. If I go into the script itself and try to run it, you can see how huge the error is. It's basically completely wrong. So I guess you need both checks. I'll try to compile it again, and if I run this, yeah, now it's showing me that it's correct here. And this is basically all completely fucked up. You know, concurrency errors are hardest of the bunch to debug. I'm not even going to bother commenting it out. I've learned my lesson. I should always be putting synchronization when crossing memory hierarchies. From global to shared, from shared to local, from local to shared, and from shared to global. This one is from local to local. It's just doing the computation. Actually, no. It's this one is from local to shared. It's storing the accumulator into the shared tensor. So we need a sync block here. Then this copies it from shared to global, and we also need a wait thread sync block, even though no obvious error is occurring. Great. I'm really happy that we got that out of the way. I've just added this one thing because we won't need to wait on the async load if it's not happening. And it won't be happening unless the beta is not 0. Now that we've come this far, what we'll do is finally start figuring out why the kernel is so slow. We're going to do a series of sanity checks, starting with making a simple memory copy kernel and then progressively making it more complicated. That way you can kind of think of it like as doing this entire thing in from the bottom up. It will be an ablation study to see exactly which piece, how long each piece is taking up in terms of runtime. We're going to see how to do that in order to really understand this kernel and figure out whether we've made any mistakes. But before that, we're going to rely on the NVIDIA Nsight tool in order to figure out whether there are any errors. And they are. I'm going to show you what the first problem is. It's I made a little mistake. And we're going to check it out right now. Okay, let's launch this thing. This is the Nsight Compute tool. Compared to Nsight Systems, this one analyzes individual kernels. It does a bunch of profiling, as you can see here. And when I look into it, I see something surprising here. The memory access pattern for shared stores might not be optimal and cause on average a 4-way bank conflict. This is a mistake that I made. It's not a mistake with the padding, but instead it's probably a mistake with the way we are factorizing the tensor. Let me show you what the most likely problem is. Okay, where is that load? Async main copy shared. Oh yeah. We have this factorize size of 16 here. We should probably get rid of that. No, actually, no. Instead of getting rid of it completely, what we need to do we'll make it byte size. Wait. Okay, I guess this one needs to come in, this argument needs to come in last. I opened the sidebar by accident. We'll put this here, and we also have this other load shared. We're going to get rid of this. Why are we doing this? This is because if we factorize a tensor, the tensor's innermost dimension into chunks of 4, what will happen is that the first thread will read it from global memory in word 0, 1, 2, and 3, and then it will store it into the shared memory in the word 0, 1, 2, and 3, which corresponds to the first 4 banks of the shared memory. So, in effect, what we are doing is letting each thread write into four banks. It will go from 1 to 4 and then all the way to 32. That is how the first 8 threads will use the banks. Then the 9th thread will go back to the beginning, to the first bank all the way to the 4th, and this will cause a conflict. If we consider how that would work for all the threads in a warp, it will result in a 4-way conflict. And now we are resolving that. I'll compile it. Let me just try running it once. It still works. And now we'll try doing the profiling again, just to see whether we've fixed it. I'll pause for a bit. And it has finished. Now let's see whether we've fixed the bank conflicts. And it seems we haven't at all. That's not good. Okay, maybe the problem is with the padding after all. Who knows? Let me pause here. I want to run this a few more times just to make sure that I'm not looking at the wrong report or something like that. I run it again and I'm looking at the details. There are some accesses, who knows where, in the source, and the only thing I can be sure of is that there are shared memory conflicts. As to how to fix them, I don't know. We're going to have to start things off from the bottom up, rebuild everything from scratch, making sure that every piece fits in place. These shared memory conflicts might be the reason why the entire thing is so slow. With a 4-way conflict, you can assume that the shared memory transfers are 4 times slower. And the shared memory being 4 times slower would make it slower than the L2 memory, which is maybe 40 megabytes large on my GPU, or 20 megabytes, I don't know, something like that. While the shared memory is only like 100 kilobytes per SM. So that's a pretty bad thing to happen. We definitely need to fix that and the various other issues. For example, it's complaining that there is some warp divergence. Let's take a look. Theoretical occupancy. It's telling that the 2 theoretical warps per scheduler this kernel can issue according to its occupancy are below the hardware maximum of 12. This kernel theoretical occupancy is limited by the number of required registers. The kernel's theoretical occupancy, blah blah blah. Okay, I'm not exactly sure what this means, because it should be saturating all the warp schedulers, but it doesn't seem like that is happening. And this is also one of the reasons why this kernel is so slow. We need to go through it bottom up. Right now, this entire program is way too complex to really deal with. I did the best effort into making this padding scheme, but it seems like it has failed, and who knows what the reason for that is. Maybe I got 1 or 2 of these wrong, but the rest is fine. But who is going to figure out where exactly the error is? We might as well go back to the previous padding scheme and simplify the program. So we'll commit tensor 9 here. And we'll move on to the next step. We'll do that as a time lapse. We'll start with the map kernel and progressively make it more complicated until we turn it back into a matrix multiply. So far, the reason why we didn't really measure the performance as we went along is in part because I wasn't really familiar with the Nsight tools. But the other main reason is that we were focused on building up the appropriate abstractions for making the kernel functionality, and right now that is basically all complete. We have the kernel running correctly. Now we just need to make it fast.
exhausted.